Hello and welcome back. Alright, today we're going to be taking a look at pointers. Pointers seem to be the tricky thing for everybody that's new to programming. And really the thing is, it's the syntax more than anything else that's complicated about it. I think if you just kind of think about what's going on and not try to do too much with them, you'll actually see that this is pretty straightforward. Alright, so what is a pointer? Well, a pointer is really nothing more than a memory address. Well, now what's a memory address? So if we take a basic look at what memory looks like in the PC, basically what you have is you have this big block of memory that's full of bits, a bunch of zeros and ones. 0, 0, 1, 1, 1, zeros. Let's put some zeros over there. Alright, and so in a 32-bit system, the maximum block size that this can be is 2 to the 32 minus 1. And so what that gives you is approximately about 4 gigabytes of memory that you can use in a 32-bit operating system. And so what a pointer is a pointer is simply the offset from 0 in that memory block. So let's say you had some data stored at that memory location. Well, the address of that location would be stored in a variable called a pointer. So when we look at memory, there are basically two segments. The first is the stack, and the second is the heap. Now this is an overgeneralization, but this is the basics of what it looks like. The stack memory is where you have your statically allocated variables. And so we see these all the time when we have functions. Alright, any block of code. Let's do int foo. Let's say we have integer x and a double y. Well, and then we have some more code. Well, this right here, these variables need to be allocated somewhere when foo gets called. And these get allocated in space made available for us on the stack. And each function, when it gets called, this section of information is referred to as a stack frame. So the stack frame is the info. I'll just do info for the function call. Info for your function. Okay, so this gets all put in the memory area, which is referred to as the stack. And the nice thing is if foo calls A, which calls another function B, and calls another function C, well, in the stack, what it looks like is there's a little foo here, then there's the A block of memory that gets allocated for us, the B, and then the C. And so there's this kind of chain. And so each one of these functions needs some sort of memory allocated for it. And when the function returns, so as it returns, this space right here gets deallocated for us automatically. So all of this right here, there's no dynamic memory allocation. There's nothing that we have to do in order to clean up our variable usages. When we start dealing with the heap is a totally different beast. The heap is what is known as the dynamic memory section. This is the place where when we want to allocate an unknown amount of memory at compile time, this is where we do so during runtime. So the one way to think about this is that the stack, this is a known size at runtime. we can look at every function call and know exactly how big that stack frame is going to be at compile time. Like, we can statically analyze that and figure that out. What we can't do is figure out when we have dynamic memory. So let's take a look at what a pointer looks like first. If we were to declare a pointer in C++ to an integer, it looks like a regular variable name, and then we have an asterisk, and then you have the variable name. Or sorry, this is the data type. Then we have the an asterisk, and then we have the name of our variable. And so this, when we read this, we call it int star ptr, or pointer, as our variable. We could create double stars. That's a U. Double star. We can call it anything we want to. Let's call it D. We can even do char stars. We'll call this str. Okay, so when we declare a variable of a pointer type, well, how big is this on the stack first? Well, in a 32-bit system, this is always 4 bytes. So this is 32 bits. So we're on a 32-bit system, and so that is the size of all of our address memories. Because remember, we have 2 to the 32nd pieces of data that we can allocate, or 2 to the 32nd minus 1 is the max size of number of items that we can allocate. So we need an integer that can fully represent all of those pieces of data. So the same thing is true with a double. Even though a double itself is 8 bytes, the pointer to a double is only 4 bytes. And same with the char. And remember, char is usually smaller, but it's still 4 bytes. Now, in the heap, so what this does is that, so let's say that this is our memory block. We have some starting point, some memory address that's starting there. Well, there's a chunk of memory. And so if this is our int star right here, well, the chunk of memory that we're looking at is also 4 bytes long, because an integer is itself 4 bytes. If we were actually going to create an array of integers, dynamically size that, we couldn't do something like this. We couldn't do int x equals 10, and then int array of x. Now, some compilers, you can get away with this, but this is not standard C++. You are not allowed to do this, because x is not a constant value. X can change at runtime. And so sure, these lines are right next to each other, and so x isn't really going to change here. But if there was a bunch of code in between, x could have changed. And so the compiler doesn't actually know how big an array should be. And so we can't actually do this. So what we need to do is we need a pointer that we want to get back. And so in C++, it's going to look like this. And there'll be some code here that we'll talk about later that will actually allocate and return it back. Alright, and so now this right here, this array, is going to point to some block, and let's just say x is 10. So that means we're going to get 40 bytes of memory. And we're going to get a pointer back to the very beginning. So the pointer, when we get the pointer back, we have absolutely no idea how big a memory chunk that we got back by looking at the pointer itself. What we do know is that we created a new array of size 40, so we need to track that size is 40 when we work with our array, so we don't overstep our bounds. Just like we talked about earlier, when we overstep bounded arrays, it's very important that you do not overwrite any of the memory that you're going to actually be allocating. Alright, so let's go ahead and take a look at how you would allocate this array variable. So let's say you wanted to create a new array of 10 bytes. Well, in C++, this is how you do it. If you wanted to create a new array of integers, you'd say int star equals new int square brackets and the size of your array. In this case, we said we wanted 1 of 10. Now instead, we could have 10 be a variable, and that would work just fine as well. So let's do that. So we have int x equals 10. Let's erase this guy over here, and let's make that x instead, just to make that clear that we couldn't do this at compile time. And so what this is going to do, this is going to call into C++ memory management libraries, go into our heap, find 40 bytes of memory for us, so that's 40 bytes, give you this address, which is the offset from 0 down here, and store that value right there in our array guy, or in our array variable. Now it's very important that when you're working with, whenever you call new, you need a matching call to delete. And when you delete an array, you need to put this special brackets and then the name of the variable that you want to return the memory to the heap. If you don't actually call this delete, well, let's take a look at what would happen. Let's say you called new and you got this much memory. So you get a pointer, let's just say you get a pointer right here, and you actually got all of this memory. Really big chunk of memory. Alright, well that memory becomes unusable to anybody else or any other call that you make inside your function. It also becomes unusable to any other program on your computer. Well, now if you never call delete, this block will never get reclaimed. So it's technically not totally true. When your program executes, most operating systems nowadays will return back this memory and keeps track of all that. But while your program is executing, this block of memory will never be usable again if you forget to call delete. And so, well, it looks really bad if you allocated half of your total memory pool. If you have lots of little blocks that you never delete, these are what are known as memory leaks. And that's bad because they can add up to a significant amount over time. Alright, so we've taken a quick look, brief look at integers. We can declare a dynamic array. We have some pointers. We have a way to delete and free up memory that we've used. We talked about the heap a little bit. So that's going to wrap it up for this video. In the next video, we're going to actually look at some code and what this looks like and dig a little bit deeper into this so that we can get a better understanding. Alright, thanks.